Namaskar and welcome to my channel. Today in this video I'm going to discuss about numericals, and the numerical is purely related to drift velocity. This numerical is a typical type of numerical, I think, because it is not frequently asked in our NEB board exams, but of course it is very important. It is simple as well and not so hard as you think. First we try to understand the questions. In the question we have given the area of cross section. Area of cross section, that means 10 to the power minus 6 meter square, and length is given as 1 meter, and density of a piece of a metal, which is 5 into 10 to the power 3 kg per meter cube, of a piece of a metal of atomic weight. We also have given the atomic weight of a metal, which is a 60. It is a 60 gram per mole, we can read. And we have asked to find first the number of free electrons per unit volume, that means electron density, provided that every atom, that means each atom, consists of one free electron, right? Single atom consists of single free electron, which is given in the questions. So from this data, first we have to find the number of free electrons per unit volume, that is electron density. And in the next part we have asked to find the drift velocity of the electrons in the metal when a current of 60 ampere passes through it, provided that the Avogadro's number, which is 6 into 10 to the power 23 per mole, and charge on the electron, the electronic charge, which is 1.6 into 10 to the power minus 19 coulomb, which is already understood. So in the questions we have given almost all the value of parameters, except we have to find out the electron density, that means the number of free electrons per unit volume, which is a small n, and finally we have to find out the drift velocity. Let's get started. This is the figure according to the questions. So in the questions we have given the length of the conductor as 1 meter, and the cross sectional area 10 to the power minus 6 meter square, current flowing through the conductor 16 ampere, and the density of the metal, which is 5 into 10 to the power 3 kg per meter cube. So in the first part we have asked to find out the electron density. So to find out the electron density, we first determine the atomic density, that means the number of atom per unit volume. Then after we will find the number of electrons per unit volume. So the electron density can be easily calculated. Since we know that the Avogadro's hypothesis is this one, which is the n upon Na equals m by m. This is the number of moles. It gives the number of mole. So the number of moles equals n upon Na. N is the number of particles. In our case, that is atom. And Na is the Avogadro's number, which is 6 into 10 to the power 23 per mole. M is the mass of the material, total mass of the material, and large capital M is the molar mass, right? So from these expressions we can calculate the formula for number of particles is n equals this one, N equals Avogadro's number, total mass of the materials, and the molar mass. This is the expression. After these expressions, we can find the number of atoms per unit volume, which is given by this formula, where N is the total number of particles inside the metal. That means in our case, first the total number of atoms inside the materials, and V is the volume. So number of particles divided by volume of the material gives the atomic density. That means the number of atoms per unit volume. Putting the value of N as we have calculated here, this is the NA M upon M, capital M, and this B, right? This B as it is. So finally we have this expression, because M by V is the bulk density of the material, simply the mass density, you can suppose. So this is our final expression for atomic density first. So putting the value of each parameters, we can have the value of Na is 6 × 10⁻23, and bulk density, that is the mass density, 5 × 10⁻³ kg per meter cube. This is already in the SI unit, and 6 × 10⁻23 is already in the SI unit. And M is the molar mass, which is atomic weight, that is 60 gram per mole. Here is the gram, this is CGS unit, so we have to convert this in SI unit. So I multiplied this by 10⁻³ and finally we have the atomic density, 5 × 10⁻28 per meter cube. That means in the volume of 1 meter cube there exist 5 × 10⁻28 atoms out there. Further, we have given conditions, that is each atom contributes one free electron. That means single atom consists of single electron. That means this number of atom consists of again this number of electrons. So the number of atoms in this case is exactly equal to the number of electrons. So we have finally calculated the number of electrons per unit volume is given by this formula, and finally we have this value. This is the electron density, right? This is the electron density, and in the next part we have to find out the drift velocity. The expression for drift velocity is this one, which is famous expression for drift velocity. So putting the value of all this parameter is, the value of I is 60 ampere and E is 1.6 10⁻⁻⁹. N is the electron density, which we have calculated here, and A is the cross-sectional area that you can see here. This is the cross-sectional area. So we have calculated the value of drift velocity, which is 2 × 10⁻³ meter per second. So from this example we have two conclusions. So the first one is, from this example it is clear that an electron will take 1 divided by 2 × 10⁻³ This is the drift velocity. As you can see here, this is the drift velocity, and 1 is the length of the distance. I suppose is 1 meter in length. So distance upon velocity, obviously it gives time, so which is equal to the 500 second. That means almost equal to the 8.3 minute. So the electron just take 8.3 minutes to travel 1 meter length of wire if it can. That means time taken by the electron to travel 1 meter length is very large. That means the electron itself has the very small drift velocity. And in the next conclusion, here is, if resistivity of a metal rho is taken to be 2 into 10 power minus 8 ohm meter. This is the supposed value of resistivity. If the resistivity of the metal is 2 into 10 power minus 8 ohm meter, the electric field inside the metal is given by this formula that we have already studied in the electrostatics in grade 11. So putting the value of this rho is this one, and this is the resistivity, and J is the current density. So value of this is the value of rho, and J is the current density, that means I upon A. I is the 16 ampere, and A is the cross section area, which is 10 to the power minus 6 we have seen here. So finally we have the value for electric field inside the metal, which is 0.32 volt per meter, and not zero. We have seen that the electric field inside the metal is not zero, as in the electrostatics. In electrostatics we had assumed there that the electric field inside the metal is zero, but in this case the electric field inside the metal is not exactly zero, because if we suppose the resistivity of the metal is 2 into 10 power minus 8 ohm meter, right? If there is no resistivity, that means if rho is almost zero, then obviously the electric field inside the material also be zero, but in this case this is not. So we have some significant value of electric field inside the material, which is 0.32 volt per meter. This is obviously not zero. So the electric field inside the metal is almost negligible, but never can never be zero. Okay, this much about this numerical. I hope you did understand. Thanks for watching.